So welcome to our Math Virtual Learning Network. We've had one convening last month, and now this is our first formal webinar, and we're going to be discussing what does mathematical understanding really look like and how do we get there in light of the Common Core. So we want to go ahead, that's my unofficial welcome that was not planned because we didn't think we would have these technical difficulties. And to go ahead and get started, I want to introduce myself. I am an ASCD faculty member, and I am in the differentiated instruction cadres and also the Common Core cadres. I'm a former high school math teacher, and I've also taught math at the university level, and am now a full-time consultant in the areas of differentiation and mathematics. And recently, I would say in the last 3 years, I've been about 99% of my work has been focused on Common Core mathematics and data implementation. So I'm curious, for those of you who have been able to hang in there, who are you? Who's with us right now? So we have our first poll question. There's some choices there with, are you a math educator? Are you a teacher leader? Are you an administrator? Who all is with us today? And so we're letting the poll go. It looks like we have a lot of math educators coming up, about 43%, 44%, almost 30% are some form of teacher, leader, instructional coach, or coordinator. We have 15% school administrators, almost 30% combined of administration, and then we have 22% are other. And last time our other were also consultants. If you are another other, how's that, another other, if you would type into your question box, what other are you? So I know we probably have some consultants. Anyone else that I don't have with us? We have some GED instructors, math teachers. So let's talk about our next poll then, and specifically what is your role, what is your job? And we have some options there for that poll question. So are you in the primary grades, intermediate? Do you teach middle school primarily, working with middle school, high school? Are you focused in algebra or geometry? So our percentages are rapidly changing here. It looks like so far we have about, this is not working, our percentages don't work out because we have well over 100% logged in here. So perhaps some of you, it says 43% are in primary, 56% in intermediate, 49% middle school, 40% high school and algebra, and 28% in high school geometry. And as math people, we know that that is not possible. So perhaps some of you are clicking more than one thing because you teach more than one, so maybe that's how come it's registering over 100%. But it does look like we have some of everybody here from kindergarten all the way through our high school grades, and that's great, so welcome. What we want to talk about today, I do want to remind you about what this virtual learning network is, and perhaps you signed up for just the webinar and you don't even know it's part of a virtual learning network or what that is. So we started our virtual learning network last month, and this is a Gates grant given to ASCD. It's a 2-year in scope, and we're just starting right now. That this first year we're going to have 5 webinars, and also the second year. And there are 4 different virtual learning networks, and you have joined the mathematics portion. They're organized by core content area, and each is hosted by a faculty member of ASCD that has some expertise in that core area. They're synchronous in that all of us are working together, all of our hosts for these networks are working together and trying to stay fairly consistent with the ideas of what's really important in terms of implementing the Common Core. And so we're trying to stay fairly consistent. So for example, we are the last webinar to go for the networks for this month, and everyone has talked a little bit about the shifts within the Common Core. All of these are being, as I mentioned earlier, recorded and archived, and you can find the archives on EDUCAURE. So our goal through this virtual learning network is to really have a constructivist community virtually. we've had a lot of comments last time about, gosh, you know, I feel so alone. I don't have other people who are working with me. We're so busy in the classroom. I don't know where to find resources. And we want to be that virtual support. So within ASCD Edge, you can join the Virtual Learning Network for Mathematics, and that's where we get to post back and forth. We exchange resources with each other, and we really just want to be a support to each other. So here's our first year. We've already had our first convening, and now this is our first webinar, and we're focusing around problems of practice. Today our problem of practice is looking at what does understanding look like in mathematics. So again, we are on ASCD Edge. I hope you'll come and join us there. And that's my little begging. Join the conversation. There's a box where you can get on Edge, and you just type right in there on what's on your mind. And this is a screenshot, so you can kind of see that the posts go below and trains go into the original post. So the last post below this one was like 25 days, but then if you scroll down, you'll see a chain of a conversation going. And so I really encourage you, please join and please post, and let's get a real rich conversation going. So today's problem of practice. Before we begin with today's problem of practice, I thought I would give you a warm-up. And let's talk about this. You've got some numbers there, 8, 4, 3, and 2. And my question is, which number does not belong, but more importantly, why? And so this is where you're going to type into your question box and give us some answers. And as you type in your answers to which number does not belong and why, I'll share those. So go ahead and start answering. Which number does not belong and why? So we have some 3 does not belong because it's odd. What else? 3, it's not a multiple of 8. Perfect. 8, it's not part of the sequence. Absolutely. 3 is not a multiple of 2. Keep going, keep going. 3 because it's not even or a power of 2. Oh, it could be 8 or 3, so why not 8? 8 because it's not sequential. Keep going, there's more. 3 doesn't belong, 2 doubled is 4, 4 doubled is 8. 3 doesn't belong because it's not a factor of 8. Great vocabulary. 8 doesn't belong, it doesn't fit the pattern of 2, 3, and 4. So we've hit 8 and 3 pretty well. Why might not 4 belong? How about 2? 4 doesn't belong, it does not have any curved lines. Perfect, it's the only digit made up of line segments. So if you use that reasoning, can you have some other arguments about the other digits? Keep going, keep thinking, more answers. 2 to the third is 8, so 4 does not belong. Again, 8, it's not in our sequence. It's greater than 5. So I'm going to jump on and say 2 to the third equals 8. That came from ARPI. So 4 doesn't belong, but here's my question for you. I could also say that as 8 is the only perfect cube, so it does not belong. If I use that reasoning, what else could you say? So 2 does not belong because it has both straight and curved edges. That's perfect for the digits. Here we go. 2 squared is 4. So I'm going to assume that what you mean by that is 4 does not belong because it's the only perfect square. 8 doesn't belong, it's the only perfect cube. I love this opener. I love this as a warm-up. You can use it with almost any age you want. Can you see kindergarten kids being able to see the sequential nature of numbers and saying 8, and they can pick up odds and evens probably. So there's a lot we can do with almost every grade level, and the more math we know, the more we can reason about it. So before I go off the screen, 8 might not belong if the base is a base 5 system. I love it. There is no such animal in base 5. In fact, it would be more like a 13. 2 is even in prime. So 2 is the only even prime number, so it doesn't belong. we could also say that 3 doesn't belong, it's the only odd prime. Oh, 3, I'm not sure about this one. We can't add 2 to the same numbers to get a 3. 2 odds to get a 3. Okay, I see. So you can add 2 odd numbers to get all of the other numbers, so 3 doesn't belong. And that's a wonderful property of even and odds. We're going to go ahead and move on from that. I'm going to circle back actually to that for just a moment. I started to say I love this because it is the great leveler. And when we think about math so often in a math class, we have those kids who kind of wait and hide in the recesses, hoping the smart kid will say what the answer is, and if the smart kid doesn't, certainly the teacher will. And they just don't feel like they can enter in. And so as you look for questions that are so wide open, this is a wonderful way to start equaling the playing field for all students to be able to enter and think mathematically. So here we go. Today's problem of practice then is how do we get students to engage with math like a mathematician? And having taught at university level, having worked with people who just kind of blow me away with their thought processes, I understand that mathematicians need skills and they need the facts, but that's not really where they dwell. And so how do we move from teaching math as a rote series of procedures and facts into really thinking about mathematics? And really it's inherent into in the Common Core with the shifts and with the practices. So in our convening last month, we actually chatted a little bit about these shifts, and we're going to take one today and look a little bit more deeply. But the shifts are this idea of focus, that we really want to go deep and not necessarily wide. The coherence part, where we think about grades and how connections are made, and we have progression documents to really talk about mathematical topics and thought processes and how they grow through the years. The rigor piece, that we really need fluency, we need application and deep understanding, all of those, that it's a balance of conceptual understanding and skill. Then we have our math practices, and that the standards themselves are prepare our kids for college and career, whatever might be next. So today, as we think about how do we get kids to understand, I'm going to zero in on this idea of rigor in the Common Core standards, and especially how it's shown through our standards for mathematical practice. To begin, I have a very quick video, and these are all found on the Hunt Institute website, which is down below. And this is talking about the importance of the understandings in math as well as skills in math, and why the content standards were written the way they were. The two speakers are two of the lead authors, Jason Zimba, and then also Bill McCollum, who is the lead author. And so here's that video, and then we'll chat about it in just a moment. So as we think about this balance of conceptual understanding and skill, and you can hear the discussion from our authors about just how important it truly is to have both of those. I know in my work across the country and actually even around the world, one of the battle cries I always hear is they don't even know their multiplication facts. And it intrigued me so much to hear that outside of our country as well, that skills are absolutely needed, but then also the reasoning, that students often can perform mathematical manipulations without having a clue what they're doing. And you say, well, could you explain that? And they tell you what they just did. And retelling of steps is certainly not an explanation. So as we think about this balance of conceptual understandings and skills, you can see them absolutely embedded in the content standards. So for example, in the conceptual understandings, understanding is used over 150 times in the content standards. The word understand in the content standard actually means understand. They're not using it as a synonym for knowing. But there's also these procedural skills and fluencies, and we call them the fluency standards because they use the word fluently. And so for every grade level, 1st through 6th, and then other states have adopted fluency standards in 7th and 8th grade specifically, there are pieces of core knowledge and skill that are supposed to be mastered by the end of the year, but then the application piece, that we really see this embedded in the real world. So as we move forward with thinking about the balance of conceptual understanding, skills, and applications, we're going to look a little bit more at the shift of rigor. And I've adapted some ideas from friends of mine, Sue Beers and Judy Carr, who wrote a leadership institute on the Common Core. And this was adapted from one of their thoughts, that we have some green flags and some red flags. So if we're thinking about rigor, then we're going to see equal intensity of conceptual understanding and skills that's going to be evenly divided. It's not going to be, we're going to teach you the skill, we're going to teach you the skill, we're going to teach you the skill, we're going to teach the skill, and oh, by the way, here's an exit card that has an understanding question. Or, and at the very end, we'll do some word problems, which is our application. Another piece of rigor is taking away the speed issue. There's quite a bit of research out there, especially coming from Joe Bowler and Stanford, that speed and time test especially may hinder math learning, not help it. That we're going to see much more authentic real-life practice, some authentic performance assessments, that it relates to the real world. And then on the other side, the red flags, there's very little, we're going to see the end of little or no formative assessment. In other words, we will be seeing formative assessment. That time tests are not a measure of mastery, and that tricks and mnemonic devices are helpful in learning, but they're not the mathematics. If it's a way to help me remember something, that's great, but that's not the mathematics. I also need to remember the mathematics. Also, green flags, that there's going to be deep conceptual understanding embedded in the assessments, that I don't do things for understanding in class but then never assess that. The counter to that, the red flag then, is strategies and fluency without any understanding. The green flag, lots of feedback tied specifically to the standards, asking kids for justifications. And the red flags that are associated with those is this idea that I can memorize steps without any reasoning or very, very weak explanation, if any. I think about dividing fractions all the time, and you've probably heard the little quip that goes, thine is not to wonder why, just invert and multiply. And we have no more of that. Then our last green flag, red flag look would be that there is fluency with number facts. I think for a while the pendulum had swung so far over to problem solving that there were some curricula out there that really did not support mastery of facts, that memorization was a bad thing, and that is certainly not the case. We need facts. We need memorization. Kids really do need to know those facts, and those fluency standards builds in the mastery of facts. That we want efficiency and accuracy. In some ways, these green flags parallel in, I don't know, 10 years or so ago, ELA went through the whole language versus phonics wars. And I always smile. My kids were going through some schooling back then, so it's a lot longer than 10 years ago. They're in their 30s now. But I remember thinking, but don't we need both? Don't we need free writing and expression, but also learning correct spelling and everything else? And math is exactly the same way. We need problem solving. We need creative thought. We need to approach problems in all kinds of directions with all kinds of representations, and we need efficiency and accuracy. Calculators I'm not even going to comment on really, because it's such a hot issue and such a debate going on on when do you introduce calculators, should kids be allowed to learn or not, and there's plenty of research that would argue both ways, to be honest. But technology, we live in a technological world. Technology is with us, and it would be a little bit like saying, sure, I understand penicillin, but I don't think we should really use it. It's kind of silly when this is our world not to use technology. However, technology should not be the reason we don't learn our facts or learn think reasonably and think mathematically. So I have another poll question for you now, And in terms of these green flags and red flags that we just looked at with rigor specifically, I'm wondering, I chose these 5 areas because I think probably they're the most broad and most that perhaps would resonate the most with you all. Which ones do you think are the ones that in your district you're doing well with? So it's which ones of these that, for example, you don't see a lot of time tests, you don't see a lot of emphasis on how fast can you do it. Which one of these is your class, your school, or your district strongest in? We're going to ask it the opposite way next. So our poll is closed right now, and it ended up that B, the authentic real-life practice and extended application, just by 2%, 34% voted B, that's your strongest area, but 32% voted D, that the fluency with number facts was going very well for you. So we're going to follow up right now and think about if these are our major green flags for this shift, this rigor shift, which is the one that you think your school, district, or classroom probably needs to focus on the most. Where do you need to go, hey, wait a sec, let's take a look at this. All right, our poll is closed, and wow, 74% went with that deep conceptual understanding and assessment. And that makes such perfect sense because I think prior to the Common Core, we always had teachers who tried to teach conceptually, but it was never really assessed. It was never made a major emphasis until the Common Core came out. And so this is a real shift for most of us in our country. So there are things, those green flags and red flags really looked at teacher actions and thought processes. Where do I need to shift away from these red flags and toward these green flags? But what about students? Because really, the teachers know how, and we try to really help our kids get to those understandings. And so I bring to you the standards for mathematical practice. I don't think these 8 standards for mathematical practice are new to any of you. However, my work in the math community, the people with whom I'm working, the people with whom I talk, writers, researchers, university, assessment directors, as I talk about the Common Core, even before they went public, as I talked about the development of these Common Core, the buzz was on the practices. Yes, the content standards are obviously very important. And the content standards tell us the what, and now they're more aligned to be internationally competitive. But it really wasn't the content standards that had everybody excited. It was these standards for mathematical practice. And prior to publication, there was actually a real debate among 2 factions in the math community about whether these should be called practices or not. And one of the arguments against calling them, I'm sorry, not practices, but standards, one of the arguments against calling them standards was that they would have to be assessed. And that came back to be the strongest point of why they had to be called standards, and that is they needed to be assessed. If these 8 practices were not going to be assessed, they would be ignored. And so the idea, the belief in the mathematical community right now is that it's the change in the classroom reflecting students' engagement with these 8 practices that will truly make the difference in math. So as we take each standard, and we're going to go a little bit faster than I had originally planned through these, we'll look at each standard a little bit more. So making sense of these problems and persevering in problem solving. So often I hear the kids don't engage, they shut down, and I remember reading, gosh, it's got to be 15 years ago, that in Japan a typical student will work 3 days on a problem before asking for help. And in the United States it was 30 seconds. I don't think we've changed too much from that. So some of the key ideas behind this practice is before working on the problem, that kids could explain the problem. They might turn and talk. You might present a problem and say, would you please turn to your neighbor and explain what this really means? They would be able to make a plan. How do you think we're going to attack this? What might work? before we start. During the problem, they're going to persevere in it. They're not going to just quit and say, I don't know. That they would monitor their own progress, that they would say, is what I'm doing even reasonable? Is this making any sense toward where I want to go? And if it's not, could I come up with a new way to go? And then after I finish, can I check my answer and my method and reflect if it makes sense? And then not only does my answer make sense, but did my process of how I attack this problem work for me? Where are some strengths? What are some takeaways that I can take away and say, as a mathematician, this was really good for me? So what does that look like in terms of students? Well, they're going to start displaying some sense-making behaviors. They're probably going to maybe show some patience and not refuse to pick up a pencil or throw a pencil down or give up too quickly. Maybe we're going to get about another 30 seconds to a minute of work at a time as we develop stamina. They're going to listen. They're going to turn and talk and problem solve and analyze the information in the problems. Maybe they'll think back and say, hey, we had a problem that was similar to this. Could we do this also? And then just keeping track of how they're doing in their learning is a huge piece of student actions. The second practice, reason abstractly and quantitatively, really has two key ideas in it, and that's contextualize and decontextualize. So we have these reasoning habits that are embedded in this reason abstractly and quantitatively. Things like creating an understandable representation. Can you show me what you did? Did you think about the units? When you looked at the quantities, did they make sense? Does your answer make sense quantitatively? Are you using the properties and the nature of operations to help you figure out what to do? So what this might look like, and again, contextualizing means I have a naked number math problem, here's some numbers, and I've worked it all out. But when would I really do this in the real world? What does this mathematics model in the real world? So I could take math and put it into context. The decontextualizing is the piece that we do so often. Here's a mathematical situation in the world. Can you suck the math out of it and solve it? So student actions then would include being able to interpret symbols correctly, putting problems into context, and also being able to interpret what the context actually means. Estimating. Estimation is a huge piece of this quantitative reasoning. Connections in the real life, multiple representations, being able to visualize a situation and then see the mathematics within that situation. And then again, as I mentioned earlier, going the opposite way, I can take a symbolic problem and put it into a word problem. Our third practice then is viable arguments and critiquing the reasoning of others. If any of you know Steve Leinwand or have read any of his books, he says this is the only one we really need, because if you can construct viable arguments, then you need to use all of the other 7. And if you can critique the reasoning of others, you have to use all of the other 7. And certainly I think this is the most fun of all of them. But the idea is that, am I arguing mathematically? Do I justify what I believe? Can I generalize an idea to other possibilities? Do I use examples and non-examples? Do I think about other representations that can either argue the same thing or dispute an idea? Am I critiquing others? Do I listen well? Do I identify mistakes and say, hey, wait a sec? Or even do I ask questions if I can't follow a student's argument? If somebody is trying to explain something, as a student, do I ask that other student, what are you talking about? What did you mean when you said? So some of these student actions, am I questioning? Do our students use examples and non-examples to defend their beliefs? Do they use mathematical reasoning and justification? Are their arguments logical? Again, those multiple representations. Is the conversation going student to student versus through the teacher? I think for me, this is one of my hardest areas, is that I tend to listen really well to a student, interpret what the student said for all the other students, listen to the next student, interpret what that student said for all the other students, and so on. So conversations run through me, the teacher, and this is what this is against. We want student-to-student conversation. Another one, modeling with mathematics, and this is absolutely huge. So the big idea here with the practices is that the reason we learn math is because math models the real world. Math gives us the vehicle to interpret and analyze everything that's going on around us. So do we represent the world through math? Do we use concrete models and symbols and pictures? Can we represent it using words and real-world language? And so some of these student actions could be just connecting math, again, to real-life situations, which refers back to number 2 as well. Can I symbolize real-world problems with math? Do I make sense of the math? Do I apply my prior knowledge? Do I look at all kinds of representations and models? Do I understand how math can help me make sense of any kind of problems situation? Then the flip side of it as well is that there are a lot of different mathematical models. And so I can use all these different representations or manipulatives or drawings or any other kind of model to help me interpret mathematically. Our 5th practice then is about tools, and the key there is, do I know how to use math tools? Do I know when to use math tools? And do I know which math tool would be of good use? And often when we think of tools, we only think of the physical tool, but don't forget mental tools, estimation, reasoning, technology, all of those wonderful things that go into applying math, interpreting math, supporting mathematicians in their endeavors to make sense. One of the little things, just as a suggestion, is instead of giving what we're going to use today to the students, for example, we're going to measure today, so here's your ruler. Often in elementary we have math boxes for groups of desks, or in my high school classroom I just had the toolbox area. I had drawers with all kinds of tools, but I never gave anything out. Students always knew they could go get the tools they thought. So one of the ways to work on this is to say, here's what we're going to do today. Take any tools out that you think you're going to need. And then work through the lesson and ask at the end, did you select correct tools? Which ones did you use well? Which ones didn't you need? Why did you think you might have needed them at the beginning? To really develop this idea that I am empowered with the tools that I choose. Precision, huge, huge, huge. I've heard and read articles that say this Common Core stuff, it's just terrible, it's fuzzy, you don't even have to get a right answer. And anyone who's arguing that in the Common Core you don't need a right answer anymore just hasn't read the Common Core. And certainly this attended precision is one huge area where you can't get away from the fact that we want mathematics spoken, read, written, and listened to correctly. So certainly calculating accurately and efficiently is essential. The correct notation, the correct vocabulary, correct units, all of these are about being precise. Often we can see that students will find an answer, and it is an answer, it's just not the answer to what the question was asking. So are we answering what is actually being asked and posed? And we're going to see that students are attending to precision, especially through communication, and vocabulary is so critically important. Mathematics is a language that is very precise and has very precise symbols attached to it. And so we want our students to carefully handle the language and symbols of mathematics as well as the computations of mathematics. Seven and 8 often run together because it makes such perfect sense. So look for and make use of structure. These are the ideas that if I understand, for example, if I understand that a quantity squared will never be negative, when I see something squared, I would automatically start thinking, well, I can eliminate anything negative in my reasoning. So I'm looking at the structure of numbers. I will point out to you in our opening, even though we're going to go to that slide in just a moment, in our opening, I asked you which number didn't belong and why. And the immediate response, and when I've used that with teachers over and over again, the immediate first response is 3 because it's odd. That's a structure. That's making use of structure. I know our numbers run in a pattern that goes even, odd, in the number line if I start with 0 and look at whole numbers going up. But can I use the structure of numbers, of operations, to make sense of problems? And so I look for students identifying, interpreting patterns and structures, being able to reason about the structure of a problem numerically to make sense. Can they break it, complex problems down into those simpler, manageable chunks reasonably? Are they looking at these complicated quantities as both a single object, for example, some huge quantity to the 4th power will always be positive. And also, I can look at what that huge quantity is and break that down into a composition as well. So do I make sense of the structures that I know in mathematics? And then very closely related is this idea of regularity and repeated reasoning. So one of the examples in the standards themselves talks about converting a fraction to a decimal. So for example, if I am converting the fraction 1/6, then I do the long division. And I get to where I'm saying, okay, 6, how many times will 6 divide into 40? And I say, oh, 6 times 36, remainder 4, bring down the 0. Another 40. Oh, 6, 36, remainder 4, bring down the 0. Another 40. Another 40, another 40. Do I see that and go, how many times do I have to do that before I go, okay, it's always going to be that? And as I do that, as I see the reasoning over and over again, we did that in our opening activity as well, and I'll point that out in a minute for you. We can start thinking about strategies based on patterns. If it will always be like this, could I just? So for student actions, instead of teaching shortcuts, we want to teach the reasoning and let them observe the pattern and say, hey, look, if this always happens, can I get a rule? Another one of these is if we're using 2-color counters and I'm multiplying integers. And I see over and over and over again through multiple representations and reasonings about a negative times a negative will always come out to be a positive. How many times will I have to model different negative integers times another negative integer to get a positive? Or will they start to see then, hey, wait a second, if there's an even number of negative signs, the answer will be positive. But if there's an odd number, it will be negative. And can they see this repeated reasoning and this patterning to make their own rules instead of my telling the rules and then trying to show them why? So these are some of the differences. The biggest key that I want to share with you this afternoon, and I realize right now that it is 4 o'clock Eastern time and some of you will have to be leaving us. But what I really want to share with you is please remember that these standards for mathematical practice, these are not what teachers are to do in the classroom. These are what students are to do. Very often I hear teachers say as we discuss the practices, I do that, I do that. Well, I hope so. You're a teacher. You're teaching math. That is not the question. The question is, do your students do this? And if they aren't, what is it I need to do to teach explicitly these 8 practices and then encourage them to engage in these 8 practices? Because without these 8 practices, understanding will become a rote memorization process as well. So I do want to encourage you. It's as I said, it is 4 o'clock Eastern time. I think I'm going to go a little bit further, and those of you who can hang with me, I would love to have you stay with me for about another 10 or 15 minutes or so. And again, if you have to leave, this will be archived. There's a classroom challenge that's shared on EduCore in the math section, and I did some screenshots here. If you haven't been to EduCore, if you click the upper bar on math, you will get this display. The one I'm going to share a video of some students, and the lesson itself is under the high school concept lessons, and I am showing some students working on interpreting algebraic expressions. So if you want to get the actual full lesson and do the activity, it's a very nice one for blending the skill and the understanding. When you click on the link, this is the screen you get for interpreting algebraic expressions, and when you come over to the sidebar menu, then you can download everything. this is a video, and I'm going to have to pop out of it, but I wanted to show you the video. I'm going to have to pop out of my screen and then pull it up for you. But I do want to show you, I do want to preface this by saying this is from the original authors, which is the Shell Corporation out of Nottingham, England. And so it's a little awkward to show this video because these are English students speaking, you know, I call them Harry Potter kids, but they have very English accents. They're in their school uniforms, and you may be thinking, well, these aren't my kids, and they're not. But the issue is exactly the same as I see every time I've done this activity with a group of students. What I'm going to ask you to do, though, is listen, and as you look at the cards, this is probably 8th grade to Algebra 1. The sort is you get an expression, and the first thing you're going to do is match equivalent expressions. Then you add word statements that express the expression in words. Then you add a table of values, and some of the values are missing, and you have to add those in. And then finally an area model, and the screenshot that you see right now is a student holding one of the area models. And as I look at that, if you look across the top, you see an n and a 6, so that would be an n plus 6 for the length, and it's by 1/2. So it would be the expression 1/2 times the quantity n plus 6. And equivalency might be n over 2 plus 3. And that's the whole activity, but they have to make sense of what does the expression really mean in these multiple representations. What we're going to see is two students, one especially that is very confused about an equivalency, and they're looking for a way to make sense of the equivalency, and the teacher does get involved. What I'm going to ask you to do, though, is instead look at this. The video is interesting, but look for those practices.
So, n divided by 2. To get it. To get it. Sam, do you get it? N and a half. Yeah, oh no, no, wrong. You see, n and a half.
Plus 6, yeah.
Plus 6.
Hang on, let me just have a look at it. Where's your yellow one for that one?
Yeah.
There. And is that part of it as well?
Yeah.
Okay,
but
right.
N half down here plus 6 afterwards. It won't be n plus 6 divided by 2. Well, it could be either of those, can't it?
I don't see why it can't be either of those.
I don't know what. But I think it'll go better then. Because it works out better.
Why don't you just move right, so don't move anything until you've made your minds up for sure. So you're saying it could be n plus 6 and a half of all of it.
Well, it could also be n divided by half and plus 6 because it's separated.
Yes, so that's the other one you want me to look at, Gemma, is it?
Yeah.
All right. So now look what that one says. It says n divided by a half plus 6. Now, is that 6?
No, it'll be 6 and it'll be 6 and a half.
Well, you're doing the area of that.
Yeah.
The whole thing's not going to be 6, that's just one side.
So yes, 6 times a half, which is...
6 and a half, 6 times... What do you mean?
Half of 6.
3, 6 times... 3.
So that's not n over 2 plus 6, is it?
No, so it would be that one.
So it would be that one. You're quite confident now. Run it through again. Lindsay, tell her again with different words, love.
I said that whole thing's not 6 because that's just 6, that line. And that's half there, so it'd be 6 times 3. So then it's not that.
Hang on, I don't understand that.
I do, because that side would be half. So the area won't be like 6, 6, 6, 6, would it? It'll be 6, 6 and half and half.
Are you talking area or are you talking perimeter now, Gemma?
I have no idea.
Right, so let's just calm ourselves down. This is the area we're talking about, isn't it?
Yeah.
If we're talking about the bit that's been zigzagged.
Oh yeah, I'm doing the perimeter.
You're doing perimeter, aren't you, love? Yes. Okay. So we're trying to decide whether both those match this diagram. Okay, so have a look at them again. You said about adding lins, didn't you? You said n plus 6 divided by 2. So this is n divided by 2.
Which is that bit.
That's a half of
Then
n.
you add in that one.
And then you're adding that. Now, is that 6? No. Come on then, Sam, what is it?
It's half a 6.
It's half a 6, isn't it?
I'm thinking, because you're saying that 6 is 3.
That could work.
It'll work out anyway,
That
because
could
them two
work
are the
too.
same.
So we're saying that this is still n over 2.
Yeah, I reckon that's the same as that.
That's the same as that.
Because that's half.
What do you think?
I think that's right.
Well, it's got to be right anyway, because it goes with that yellow piece.
So have you put it with that yellow one?
Yeah. Them two were the same.
So do you want to check now that that goes with that?
So what we're doing, and it's 3.
Yeah, just do 3 because that's it.
So it's 3 plus 6 divided by 2. Right. It didn't work.
How did you get?
I got 6 for that, and 4.5 is number 3.
So I went ahead and stopped the video. The last part of it is very interesting. She uses her calculator to check to see if the table will work for the 2 values, but doesn't use the calculator correctly, and then she's more confused than ever. There is a lot going on in that video, and so what I'd like you to think about as you saw that video, which of the practices were being exhibited by the students, and specifically when. And so I'm going to ask you to go ahead and type in, as you think about that video as quickly as possible, what else do you see? Okay, so here we go. Definitely practice number 1, there's perseverance. Absolutely. Justifying your thinking and critiquing the reasoning of others. I loved it when the peer in the group was helping the one girl who was really struggling with what it was. So we saw justification of thinking and critiquing the reasoning of others. Modeling, absolutely, all those different representations, persistence, the models, the tools even, using the calculator even though it wasn't used correctly at the very end to check the table, but then also the reasoning about what does that model really mean and how is 6 times 1/2, and even though they misspoke several times in there about being divided by 1/2, I wish we could go back and edit, but that's what was said. Chance to think and discuss it with another student. There's that 3 again, constructing arguments, reasoning, 1, 3, 4, 6, and 7, wow. So we saw so many of those practices in action. And I think often that, I'm so sorry, I'm going wrong. So often we have these great activities and we guide them just a little bit too much. If you've ever seen Dan Meyer's TED Talk that launched him into his fame called Curriculum Makeover, he has just one little phrase in there that I just love so much. He says, he almost toward the end of it, he says, be less helpful. I think we need to be less helpful for our kids so our kids will pick up the reins and engage in those practices. I was going to ask you, but because of time I'm not going to. When you think about that warm-up I did, there's a reason I did the warm-up. And I was hoping that you would see that that warm-up hit almost every single practice. So certainly the perseverance, I wouldn't let you stop after 3 is odd. We kept going, and actually there's so many more answers that we could have gone to. So for example, symmetry. 8 is the only one that has more than one symmetry. 3 has horizontal symmetry, but 8 has horizontal, vertical, rotational point symmetry. We could have talked about 8 is the only digit that has a closed area. There's all kinds of ways we could go with it. So the persistence piece. The quantitative and qualitative, we were looking at sequences. We were looking at 2 cubed equaled 8. Certainly all of those. For 3, the arguments, we were certainly having to justify any time we said which one didn't belong, so there's our constructing logical arguments. With 4, the modeling, that one may not be as much, but if we had a number line there and we said, look, at 8 doesn't belong, it's not consecutive, and we used the model line to show it, there's our modeling. So for 5, tools, if we started thinking about estimating or what other tools we might use to figure it out, maybe we had a multiplication chart to look at how things could be related. Or we were thinking of similar problems. Those would all be tools. 6, precision. Boy, do we have precise vocabulary. When we talked about primes, evens, odds, We talked about factors and multiples and all of the vocabulary that came out, as well as the correct computations that came out. For structure, we were looking at evens and odds. We were looking at consecutive numbers, the way our numbers work, and then patterns. When I said, hey, if we take 2 cubed and we talk about 8 doesn't belong because it's the only perfect cube, then right away we got 4 doesn't belong, it's the only perfect square, and there's our repeated reasoning. So even a simple warm-up like that can engage all of these practices. So I thank you for joining us, and again, I'm so sorry for all of these difficulties that we have had. I'm going to encourage you to, if you have questions that I wasn't able to answer, I am on Edge at least every other day in our VLN. Please join, post your question there. I will write you books, I promise. As I think about our next steps, if you have any more interest, I did post this, it's in the train if you want to look at the train on the VLN. This is an old webinar, I think I did it a year ago, November, that looks at understanding more from an understanding by design or differentiated instruction curriculum clarification viewpoint, but talks about content standards and say, how do I take my content standards and make courses out of them? Design scope and sequence, develop units, write these understandings. So there's a webinar that's archived. That's the link to it if you want to see that. And I look forward to working with you until our next webinar. So please go to Edge, join our VLN, post. Let's get our dialogue going. And our next webinar is next month. It's Friday again at 3 o'clock Eastern Time, and hopefully we'll be right on time, February 21st. So until then, thank you so much. I look forward to talking with you on ASCD Edge.